The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
So today, actually, I'm going to be presenting what is my next book, which is called Why Information Grows, and it's coming out on June 2nd. It's already in Amazon. It's coming out in English, German, and Chinese, but hopefully in the future, we're also going to get to enjoy it in Portuguese, And the story of the book, actually, is quite simple, The idea is that the universe is made of three things, Energy, matter, and information. But information is the one that makes the universe interesting. Information is the one that gives the universe its structure, its beauty, and its complexity. But for the most part, we don't know what information is and where it comes from. So what I'm going to try to show you today is the path that the growth of information has to follow from the beginning of our universe, to our modern society. And to start, that journey, I'm going to start by looking at how information grows in physical systems. Because believe it or not, the growth of information, the growth of physical order in the universe is actually not trivial. So the first part, is bits in atoms. Information actually is physical, and understanding, the origins of that physical order was not that easy. And one of the men that tried to understand the origins of that physical order was Ludwig Boltzmann. So Boltzmann was an Austrian scientist in the late 19th century, but he was also a very unhappy man. Do you know why I know that Boltzmann was an unhappy man? Because he killed himself. That kind of gives it away. So he was a man that late in his life, he had a lot of troubles, he had difficulties with his colleagues, he also had a son that had, died recently, and late in his life, he killed himself. But before that, actually, he had also had a great scientific struggle that was a little bit more internal. Because actually Boltzmann was a late 19th century scientist that was inspired by a couple of very prominent mid-19th century scientists. So I don't know if you guys remember, but in 1859, Darwin publishes The Origin of Species. And Boltzmann does most of his work on the late 19th century, and he was deeply inspired by Darwin and Wallace because he saw that the theory of evolution through natural selection that they had advanced was a theory that helped explain the biological origins of order. There's a lot of order that was observed in biodiversity, and Darwin and Wallace had been able to explain that order through their theory. So Boltzmann said, well, I want to take this to the next level. I want to explain the physical origins of order. And he started to think about how systems that are made of many particles were going to behave. And what he discovered is that actually the universe has some sort of hostility towards order. The universe doesn't like order. So what Boltzmann did, his big contribution, was that he developed the statistical foundations of the second law of thermodynamics. And the second law of thermodynamics tells us that entropy in our universe always increases. So what does that mean? So basically, the second law of thermodynamics, in simple, is just a tendency of our universe to average itself out. So if I take hot water and cold water and I put it together, I end up with warm water. And I cannot unmix that heat. If I put milk, into my coffee, at the beginning I have some beautiful swirls, but at the end I have just kind of like this hazy, milky cloud. The second law of thermodynamics is also like the reason why when we speak, that sound is so transient because as soon as the sound leaves our voice and it starts traveling through the air, those molecules of air don't want to encode those pressure waves that actually are making, that sound be transmitted. They average themselves out and that sound disappears. So the universe has a fundamental hostility towards order, and Boltzmann found that, and eventually the question of where order comes from, what are the physical foundations that give rise to physical order in the universe, remain unsolved. And this was a question that actually was explored by people like Einstein and Gibbs that made the contributions, to statistical mechanics that came after Boltzmann, but the real breakthrough happened a little bit later. It happened when the Russian-born physicist Ilya Prigozhin started to do work in out-of-equilibrium statistical physics. Because basically Prigozhin reasoned that Boltzmann was right. When you have a system and you're looking at the final state of that system when all of the action already happened, that system is going to go into an equilibrium in which basically there's going to be no structure and everything is going to have averaged out. But in reality, the things on Earth that beget order or that epitomize order are not things that are in that equilibrium. Our planet, for instance, has been out of equilibrium for billions of years because it is powered by the sun and it's powered by the nuclear decay that is happening on the Earth core. Our bodies are definitely out of equilibrium. Every day we eat and do something else to have a flow of energy through our body that help us remain out of equilibrium. Equilibrium is death. Yeah? So Prigozhin starts thinking about, well, if you have a system that is out of equilibrium, what are the physical laws that the systems need to fulfill? What is the objective function, the utility function of a system that is out of equilibrium? Boltzmann had showed that for equilibrium systems, that utility function was the increase of entropy. Basically, systems maximize entropy. What Prigozhin showed, in a very particular case, though, that when you had a system that was out of equilibrium, the system did something different. It didn't maximize entropy, it minimized the rate of entropy production. That means that the system produced entropy, but produced as little as possible. Okay? So what's an example of that? So I assume most people here have used a bathtub once or twice in their lives. And when you have a bathtub and that bathtub is full of water, that bathtub basically does not encode much order because the molecules of water inside that bathtub are going around willy-nilly in random directions. But now let's take that bathtub out of equilibrium. Let's remove the plunger. And we remove the plunger, basically gravity starts sucking, water down the drain, and the water on top of the drain self-organizes into a whirlpool. That whirlpool, is a steady state of a system that is out of equilibrium. And that steady state of a system that is out of equilibrium actually dissipates very little energy and contains information. Why? Because the molecules that are going down that whirlpool actually are going down with velocities that are very correlated. A molecule that is going down the whirlpool right here is going to have a very similar velocity than the one that is right next to it. And because of that, obviously, there's less dissipation, so the system is not producing as much entropy, and at the same time is forming what Prigozhin called a dissipative structure, okay? Which is the structures that form in systems that are racing down towards, that are out of equilibrium and that converge into these steady states. And these steady states that have these correlations are the beginnings of the origins of information in the universe. But the lesson that we have to take from Prigozhin actually is even more fundamental than that. Prigozhin tells us that to have order in the universe, we need to pay a price. You need to spend some energy. You cannot get order for free. So there's a fundamental physical relationship between spending energy and generating order. You cannot generate order if you don't spend energy. The problem, though, with Prigozhin's ideas is that they help us explain these simple forms of order. They help us explain, the order that we observe in a whirlpool, or that astronomers could observe, in the vortices that form in the surface of the sun. But it cannot help us explain the complexity that you and I are used to every day, the complexity of life and the complexity of society and economy. So there must be other loopholes that the universe is using to help order grow beyond the order that we observe in such a simple system. And one of these loopholes was hinted at by Erwin Schrödinger in his 1944 book, What's Life? So in What's Life, Schrödinger already understands that life is a machine that is basically battling constantly the second law of thermodynamics. It's trying to generate order, and for that, we eat and we do something else. But what Schrödinger reasoned is that, in some sense, generating order is kind of expensive because the second law of thermodynamics is always there. It's always trying to take that order away from you. So for life to be effective, for life to exist, it has to have some mechanisms that allow that order to endure, to be shielded against, the clause of entropy. And that is the existence of solids. So proteins and DNA and RNA, they're all aperiodic crystals that are able to preserve information in some cases for relatively long periods of time. DNA is a very stable molecule. And because we have these solids that are able to store this physical order, that are able to store this information, we do not need to produce it constantly. We can save it, and then we can recombine it, and then we can create more order. So the second ingredient is the existence of solids. The third and final ingredient that I'm going to present to you guys here is the computational capacities of matter. So for the growth of information in the universe to truly explode, matter needs to develop a capacity to compute. Actually, life is a consequence of matter's computational capacity. And to give you an example, I'm going to use an organism that you usually don't think of as a computer, which is a tree. Most of you probably don't think of trees as computers, but trees are computers. Trees know in which direction to grow their leaves and in which direction to grow their roots. Trees know when to turn genes on and off to fight off pests. Trees know when to shed their leaves and when to grow their leaves. So even though a tree doesn't have the type of consciousness that you and I have, and even though it doesn't even have a nervous system, it is a computer that is able, to perform relatively complex computations, like the ones that are involved in fighting parasites, or even the process of photosynthesis, which is actually not that simple. So together, these three mechanisms help explain how we can form these little pockets in the universe in which we go against the second law of thermodynamics and we allow order to increase. First, to generate information in the universe, to generate order, we need to be in an out-of-equilibrium system. There is an energy cost. Second, we need to have some solids. We need to have some way of storing that information so that then we can recombine it, and we can use it again. And we don't have to generate it all the time. Third, matter needs to develop that capacity to compute. So by using energy and these solids, matter is able to transform order into more order through these different type of computers like your cell or a human and whatnot. So what I'm going to do next is I'm going to try to unpack these ideas in the context of society and the economy. We just saw what are the basic physical principles that allow order to exist in the universe, that teach us that actually the growth of order is not contradictory with the second law of thermodynamics, but they don't go too far to try to explain the order that you and I might be interested in, which is the order that evolves in society and the economy. So the next question that I'm going to ask, is, well, what is the order that actually is important in the economy? And for that, I'm going to tell you a story. So as an expat, I usually go and visit my home country's newspaper when I'm in the US. So I went one day to the newspaper, and I saw a news article that said, Chilean bought the world's most expensive car. And obviously, my first reaction was, what a douche, But then my later reaction was a little bit more thoughtful and said, well, the most expensive car, okay, what car is that? Okay, it's a Bugatti Veyron. How much does it cost? Well, it costs $2.5 million. How much does a kilo of Bugatti Veyron cost? Okay, $1,300. Well, that's worth more than a kilo of silver. So in some sense, it's a pretty expensive car by the kilo or by the pound. So now I'm going to invite you to imagine that you just won this really expensive and fantastic car. You're driving it down the road, and you make a bad maneuver, and all of a sudden, boom, you crash it against the wall. Okay? So obviously, you don't need a PhD in economics to realize that the value of the Bugatti evaporated the second that you crash it against that wall. But what this physical experiment did? Well, obviously, a car crash does not destroy atoms. It's not like a particle accelerator. Even though the car might be fast, it's not that fast. But what it did is it changed the way in which those atoms were arranged. It changed the order. And that tells you that that car was not made of atoms, was actually made of information. So to understand the information that actually is relevant in our economy, I'm going to now invite you to compare apples and apples. Okay? On your right, you have the apples that you eat and you buy in the supermarket. And on the left, you have the apples that you use to check your email, Yik-Yak, Snapchat, whatever social media you use. Okay? And the question I'm going to ask you guys here is, what is the true difference between these two types of apple? And some people can say price, some people can say complexity, but I can very easily argue that the biological apple is actually more complex because it has some internal molecular mechanisms at the cellular level that are unparalleled by the ones that can be executed by the apple that you use to check your email. The true difference between these two products, is not that one contains information, the other one doesn't. They're both rich on physical order. The difference is the origin of that order. Because the first apple existed first in the world and then in our heads. There were apples before we had a name for an apple, a market for an apple, or a price for an apple. The second apple existed first in someone's head and then in the world. And that tells us that this second apple is actually a crystal of imagination. So this is actually quite peculiar because it tells us that in our society and in our economy, we actually are constantly in contact with information that was begot originally as part of a mental computation that existed virtually in a human. And that is actually not that trivial, because if we look at two different office environments, for instance, this is how an office environment might have looked like in most parts of the world like 50,000 years ago. This is an office environment in which actually is quite information rich. All of these people are full of information. The plants obviously contain information in their DNA and their cells and their structure. The soil is rich in bacteria and an ecosystem that embodies a lot of information. So the difference between that office space and this office space is not that the latter has more information, it's that the origins of information are different. In the second one, all of those objects were imagined before they were built. In the first one, the origins of the information that was embodied in those people and in the objects that they had access to were mostly biological. And this allows us to interpret some economic process in a new light. So for instance, let's look at the exports between Chile and South Korea. And this is from the Observatory of Economic Complexity, a tool that we built at my lab at MIT. And here you can see, for instance, that Chile exports $4.6 billion to South Korea. But also you see what Chile exports to South Korea. And you see that this is mostly atoms. Okay? Now let's see what South Korea exports to Chile. So South Korea exports to Chile only $2.5 billion. But while Chile has a positive trade balance with South Korea, it has a negative imagination balance, because Chile is exporting atoms and importing back the way in which these atoms are arranged. And that is information. Also, when we think about the world in terms of imagination and information, we realize that some dynamics of exploitation and rhetorics that sometimes we do have here in Latin America, are actually quite the opposite. So, for example, Chile makes most of its money out of rocks. These are these green rocks, copper rocks. And the question is, why the heck would anybody want to pay money for rocks? In the case of copper, we all know the answer now, is because basically you can take copper, make it into copper wires, and then, why do you need those copper wires? Well, they're kind of like a cheap way to transmit electricity. Gold is a little bit better, but copper is kind of a cheap electrical conductor. So in some way, the world has been electrified with copper. But then, where does the value of those rocks came from? Well, the value of the rocks came from people like, Michael Faraday, that centuries ago, like a century ago, realized that actually if you jiggle a magnet inside a coil, you can generate electricity. So in some sense, the dynamics of exploitation is not one in which, Chile is being exploited because people is coming to take those rockaways, but it's one in which the imagination of those that were able to realize, how to produce electricity and what were the laws of induction, endowed those rocks with economic value. So the question is now, why do we crystallize imagination? I don't know if you guys have thought about it, but if you ever thought about that question, like what makes humans different from other species, the answers are very simple and we have lots of them. Humans build cars, they do figurines in blown glass, they build circuses. There are a lot of human activities that obviously animals don't do, because what humans do that animals don't is that actually we create crystals of imagination. We create objects that were born first as mental computation. So we're kind of unique in doing that in our planet, and actually there's a big cost of doing these things. So there must be some sort of benefit that explains why we go to great lengths to do it. Because if there would be no benefit, why bother? So to answer that question, to explain you what are the benefits of crystallizing imagination and why we do it, I'm going to ask you another question, which is, how many of you use toothpaste today? How many of you use toothpaste today? Okay, no, sir? No? Okay. So now keep your hands up if you use toothpaste today. And now keep it up only if you know how to synthesize sodium fluoride. So you realize there that when you are using toothpaste, you're not just buying some atoms in a tube. What you're buying is access to the practical uses of knowledge and know-how that you don't have in your bodies, but that exists in the bodies of someone else, that you get access through in this product. So in some sense, you have to stop thinking of information only in terms of messages. Because on the one hand, sure, I can encode order in air to communicate a message like I'm doing in this talk. But in many occasions, actually, the way that the economy works is that we encode order in objects, not to communicate messages, but to make accessible to others the practical uses of the knowledge and know-how that we use in creating those projects. Okay? So to finalize this section, I'm going to borrow a story that was hinted at by Norbert Wiener in his weirdly titled book, The Human Use of Human Beings. Okay? And this book, like Wiener said, you know what? Ants are not very smart. They're not a very smart animal. But when they come together, they can do amazing things. They can solve problems of transportation and routing and whatnot. How do they do it? And the answer actually is quite simple, that ants, just like us, share an important property of social species. They have the ability to poop information. Okay? So ants, when they walk around, they can leave chemical signals behind them, and the other ants use those chemical signals to coordinate activities collectively, and then they're able to solve problems that obviously escape the capacity of an individual ant. So this ability to deposit information in the environment is the one that allowed groups of ants to be so much smarter than individual ants. And we are like ants in some way because we're able to deposit information in our environment. But unlike ants, we don't have a fixed repertoire. The information that we can deposit in our environment is not encoded in our genes, but it's the fruits of our imagination. So actually, we have a much larger repertoire, and because we're able to crystallize imagination, we're able to deposit information in our environment that came from mental computation, we're able to create a society that is, of course, much more complex than those of ants. So hopefully, I have shown you that first, the origins of information in the universe are not trivial. Second, that nature has some very well-defined loopholes that allow information to grow in certain pockets of the universe. Third, that economies are actually made of information, that products are made of information. And fourth, that the origin of the information that is embodied in products, actually those mental origins are important, because eventually those allows us to create products that communicate the practical uses of knowledge and know-how. Now, what I have to try to explain you is, well, how do we do to create those products? Okay? How do we organize ourselves to do that? Because in some sense, these products are these packets of information, and someone has to be able to compute that. So how do we organize ourselves as a collective computer to help information grow? And for that, I'm going to tell you another story, which is the story of Pep Guardiola's visit to the MIT Media Lab. So how many of you here have heard of Pep Guardiola? No? So Pep Guardiola at that time was between jobs. He was between being the head coach of Barcelona to being the head coach of Bayern Munich. And he was living in New York, and he had a friend at MIT that invited him to visit, and he wanted to see the Media Lab. So Joe Ito, the director of the lab, said, Cesar, could you organize a visit for Pep Guardiola? And that was kind of easy because all the students wanted to meet him. Okay? So we took Pep around the lab, he saw the demos, he saw the projects. But during that week, as we prepared for the meeting, a bunch of Spaniard students have heard rumors that Guardiola was coming, and they say, Cesar, we want to meet Pep, And obviously the meeting, we had to keep it a little bit on the hush-hush because, we didn't want any media or any stuff like that. It was going to be like a more intimate event. So I said, guys, show up at the lab, and then when we finish the tour, we're going to sit him down, and we're going to do a Q&A session, okay? So, there was like a little stage there. We sat him down, and the student sat down, and then a student asked him, Pep, here at MIT, we do a lot of robotics. So my question to you is, and the student had like this, like he was all excited, So my question to you, Pep, is, if we build a team of robots, would you come and coach it? Okay? And Pep thinks for a little, and he says, well, you know what? The most difficult thing of coaching a soccer team is not figuring out a game plan, but it's embodying that game plan in those players that take the field. Since in the case of the robots, I don't see that as a challenge, I'll decline your offer. Yeah? So basically what Pep is saying is that eventually what makes sometimes the execution of complex tasks difficult is the fact that, we need to work together to accomplish them. And the question is, why is that? Wouldn't the world be much happier and simpler if we could do everything by ourselves without having to go through all of the distress and emotional, exhaustion that comes with social interactions? You know, why do we have to, work together? You know, and the reason actually, can be explained by answering the question, how long does it take for a person to become a dentist? So how long do you think it takes for a person to become a dentist? 5 years, 5, 6 years? Well, I would say 30, because the person needs to learn how to walk, how to talk, how to do math. And by the time they're already in dental school and they graduate and they have some experience and they've done the stuff, they're kind of 30, their brain is half frozen, and there's not much maybe that they're going to be able to learn in their lives. And what this is illustrating is that all computational systems have a finite capacity. Whether it is a cell, a human, a synthetic computer, they all have a finite capacity. And what this implies is that at some point, as we accumulate more knowledge and know-how in our society, as we increase our capacity to compute, we're going to get to a point in which the things that we're making require a computational capacity that is larger than the one that you can fit on a single human being. And at that point, you are forced to divide that computation up. You are forced, to divide that knowledge up. And at that point, when you cross that person byte limit, the person byte being the maximum amount of knowledge and know-how that you can embody in a human, the economy can only survive if it's computing the products that it's making through networks of people. Okay? So the question obviously here is, what determines the size of these networks? Okay? Apparently these networks are important because these networks are the embodiment of the computers, that make the economy possible, that make the products that we make, possible to make. And one of the people that started thinking about this is Ronald Coase. So Ronald Coase was, 22, 23 years old, and he was at LSE at that time, and he went up to this seminar from this Department of Commerce professor, and he heard one of these sentences that economists love to say, and they always piss people off, which is, the normal economic system works itself out. And that sentence kind of pinballed inside Coase's head, because notice that Coase was born in 1910. So in his early 20s, he was actually right after the Great Depression. And what he observed, in his life as a normal human being was that the economy was not kind of like this, bakers and butchers and horseshoe makers exchanging things harmoniously thanks to the price system, like in a Disney type of cartoon. It was, a world in which basically people were in very dire economic conditions, and the world was controlled by very hierarchical structures that were very insular. And when a worker moved from that, job to that job, it was not because the price system, had worked its magic. It was because the boss told him, Jimmy, now you work there, and Jimmy would not say a word. So he said, well, actually the economy is made of these other units, and people had not tried to understand that much, what makes these units and what determines the size of these units. So he came up with what is known, in economic literature as like the traditional theory of the firm, or Coase theory of the firm. And the idea is that if you're going to do something in a firm, you have always the option to buy or to make. And at the point in which those two options equilibrate, the firm stops growing because you prefer to buy rather than make. But what's going to be more insightful for us, is that actually also Coase comes up with this idea of transaction cost. And what he hints at is that, well, if you have a network, there are costs to the links that you have in that network. Okay, links are not free. They require time, they require effort, they require communication, they require energy. Whatever you want to put as cost, they require a cost that is non-zero. And if the cost is very little, you can have many links, and therefore you can form large networks. But if the cost is very large, well, you can have very few links, and networks are going to be small. So in some sense, what is the general lesson from Coase theory here that I want you guys to extract is that the size of the networks that we can form is inversely proportional to the cost of links. Obviously, just like Coase was motivated by being pissed off, at one of his professors, sociologists sometimes get motivation by being pissed off at economists. One of the guys that actually then was not so much in agreement with the way that economists were understanding networks was Mark Granovetter. Because, well, it's true that you can think of a system in which maybe, someone has something that I want to buy, and we find ourselves through the magic of the market, whatever that is, and we have that transaction, and therefore links are an epiphenomena or side effect of economic activity. But Granovetter said, you know what, that's kind of bullshit, because people are not born into markets. People are born into families, and then they go to school, and you have to become friends with whatever kids are in the same class than you, and you're going to maybe spend 13 years with the life with them. So what Granovetter is saying is that while, sure, economic incentives can help people create links, society comes with a lot of pre-existing structure that predates economic activity. Social networks are older than currency. Okay, there were social networks in the world like tens of thousands of years ago. And he said, and this pre-existing economic and he says, this pre-existing social structure is important for economic activity because actually the way that the economy is the other way around. It's not that the economy begets links as a side effect, it's that these links determine what economic transactions are possible. So basically, the economy was embedded in a social network. The social network was the pipes that allow, economic flows to occur. So obviously, he had to put his data where his mouth was, and what he did during the late 60s was that he did a very large survey of how people got jobs. He said, well, I want to try to show that this is the case, that pre-existing social structure matters for one market, and that is the labor market. And that is an important market because that's the market by which people add people to their networks so that they can compute things together. And what he found is that basically 50% of jobs are given to a friend of a friend. That pre-existing social structure actually determines 50% of job allocation. And there were thousands of papers that later reproduced this type of findings. Here is just 3 of them, and it's more or less consistent across the globe and even across different types of group, 50% of jobs, are assigned through social networks. What is interesting though is that, have you thought about which 50% is the one that's assigned? It's not the 50% of shitty jobs. It's the best jobs are the ones that are assigned through social networks. So if you're looking for a CTO of your company or a CEO of your company, the probability that that person comes through a recommendation from a friend of a friend, from someone that you know, is really, really high. If you're looking for someone that is doing like a commodity service type of job, usually those people tend to be hired by the market, meaning like an ad on a website or a newspaper. Okay? So, Granovetter shows that there's all of this pre-existing structure, and social networks start becoming relevant, in understanding the networks that we form to create things, So eventually one person that adds even more, to the important social networks is, James Coleman, but also Francis Fukuyama in his book, Trust. So the interpretation that Granovetter, Fukuyama, Coleman, all of these social capital theory guys arrive at is that, well, social networks are kind of the structure in which our society deposits trust, confianza. Why? Because, well, a social relationship is only meaningful as long as we trust each other. Yeah? If I know of you, but I think that you're going to stab my back every time I turn around, that is not a meaningful social relationship. For us to be able to do something together, I have to trust that you're going to have my best interest also in consideration. But the thing is, not all societies have the same amount of trust. So what Fukuyama says is that there are some societies that are high trust societies, and there are some societies that are lower trust societies. And trust is kind of like the inverse of the cost of links that Coase had described. So if you're having a low trust society, the cost of links is very large because you're thinking that the person is going to screw you, so you better be a really good friend with someone before you do something together. You need to build up relationships very much in a low trust society, to be able to trust someone. In a high trust society, actually, you can do things with people without having to develop the relationship that much, so the cost of links is lower, And what it means is that, well, in low trust society, you're going to be able to have little networks, and in high trust society, you're going to be able to have large networks. So what are the examples of these low trust societies? Fukuyama called them familiar societies. Why? Because when nobody trusts each other, they trust their family. That's the last reservoir of trust that societies generate. And these are like the Don Corleone, societies in which like economic activity is dominated by small networks of kin, people that belong to the same family. And these small networks of kin, obviously, they have a very limited pool of talent. Because obviously, you might have a lot of trust in your brother, but your brother might not be very smart. Okay? And since you're only restricting, the management of your company to people in the same family, the network is small, it has a limited pool of talent, so it's going to gravitate to an activity that you can manage with a relatively small pool of talent, which are simpler economic activities, like agriculture, mining, retail, even finance. Yeah? These are also societies that when people come together, they tend to protest. They tend to demand from the government, rather than try to self-organize to provide their own solutions for the things that are lacking. On the other extreme, we have trust societies, okay? And in trust societies, people form large networks of non-kin. Okay? These are large networks in which the people that are involved are not related by family. So think of Steve Jobs and Steve Wozniak and Johnny Ive. They were not three brothers, they were like three people that have like a set of complementary skills that was fantastic, And in these societies, you create these large networks of non-kin that gravitate towards much more complex industries. Okay? So they gravitate to aerospace, microprocessors, pharmaceuticals, etc. These are also firms in which the people that are on top are inventing the things that the firm do, not just administrating the way that things work. Okay? So it's a little bit like the reverse. If you're in a simple industry, the boss is a manager. If you're in a complex industry, the boss needs to have a vision, needs to be the inventor, needs to be an Elon Musk, a Steve Jobs for that industry, for that company to be able to do well. And these are also societies that self-generate instances by which people accumulate social capital and actually are able to develop the networks that they use to create things. So we've seen like three different theories that complement each other and help us explain the size of the networks that we're able to form. But there's something that they have in common, that no matter if the size of the networks that we form is limited because we have pre-existing social structure, or because there are transaction costs, or because there are limited levels of trust, what we're going to have is that the size of the networks that we're able to form are finite. And that finiteness, once again, tells us there is a second quantization limit. Once again, just like a human runs out of capacity to compute, to create complex things, to create products, like a network is also going to run out of capacity. And we're going to get to the firm by limit. So what this tells you is that as we keep on accumulating knowledge and know-how, as our society keeps increasing the computational capacity, we're going to go, from a world that is dominated by people to a world that is dominated by networks of people, and eventually to a world like the one that we live nowadays that is dominated by networks of firms. And that's just an example of products that eventually exist only in the context of networks of firms. Think of the computer. The computer obviously has a brand, but the many parts that make that computer come from a complete ecosystem of different companies. And then the software that you run on that computer and that actually makes the computer useful to you, many of those pieces of software also come from a lot of different other companies. And the websites that you visit when you are in your computer are produced by yet another group of people. And the products that are being advertised in the websites that you consume when you're using your computer are yet produced by another ecosystem of people. So in some way, what we have now is a world that is dominated by networks of firms that allows us to generate very long loops, include a lot of people, and eventually create a very complex economy. So what I'm going to say here is that Pep was right. That eventually what makes, the achievement of difficult things, whether it is winning the Champions League, which is not going to happen for him this year, or producing a complex type of product, what limits those type of achievements is the ability to embody computation in a group of people. So to conclude, I'm going to show part 4, which is where I bring data in to try to explain some of these things in the context of macroeconomic data. And to do that, I'm going to first introduce a distinction between genotypes and phenotypes. Okay? So genotype is the DNA that I have inside you, is that genetic information. Phenotype is how you look or what diseases you have. And the problem is that mapping genes is kind of difficult, or historically was very difficult. Now it's becoming simpler. But mapping phenotypes, especially for some of them, is actually quite simple. So what we can do in this type of systems is that, well, let's say that we want to know if someone has genes for being tall or being short. Trying to figure out what are the genes that encode for height is difficult. But if I tell you, well, one of these persons is Danny DeVito and that one is LeBron James, you probably can have a very good educated guess of who has the genes that encode for height and who does not. Okay? By the same token, the economy is made of knowledge and know-how. the one that we use to compute things collectively. And what we produce is information in the form of products. So since measuring knowledge and know-how is kind of difficult, what we can do is try to proxy that by looking at the mix of products that different places or regions make. And there are some facts that come out when we start looking at data that connects countries to the products that they make. So the first one that I'm going to show you here is here you have a municipality industry network and a country product network. So the first matrix has a black dot for every municipality that has a presence of a certain industry in Chile. And the second one has a black dot if a country exports that product. But you see that these matrices have kind of like a weird structure. That's because I sorted them. I put at the top the municipality that is more diverse, or the country that is more diverse, and I put on the left, the product that is more ubiquitous, or the industry that is present in the largest number of locations. And when you do that, you get this nested structure. And what does this nested structure tells you? Well, it tells you that the places that do few things, are able to produce subsets of the places that are able to do more things. They're not making different things, they're making subsets. And why is that? Well, because the places that are making a lot of things are places that are able to create the large networks that you need to make those difficult things and the simpler things that are being made in the places that are making few things. Okay? So you see how kind of like that is, like a mapping of this difference in the gradient of the sizes of the networks that people form. So that's one, fact that comes out from the data. The second fact is that economy is diversified towards related varieties. So if I know the mix of products that an economy makes, I can actually very accurately predict what are the mix of products that are going to export in the future. Why? Well, because as people accumulate knowledge, and accumulate know-how, and that is difficult, and they have to grow the networks that they use to compute things, it's more easy for that people to add knowledge that is complementary to the one that they have, and that knowledge is going to lead to an industry that is similar to the one that they're in. So to illustrate that, I'm going to show you like a couple of quick visualizations from the Observatory of Economic Complexity, which is one of our data visualization sites that we created at MIT. And here we have the productive structure of Chile in the year 1979. And the products that are painted are the products that Chile exported in that year. The ones that are light gray are the ones that they did not export. And you see here, the structure of Chile is quite concentrated, for example, in this blue fishing cluster and in this yellow processed food cluster. But in 1979, Chile did not export vegetables or fruit juices. But they export many products that were similar to those, that were related to those. How do we know that? Because we know the probability that two products are co-exported. So what we're going to do now is we're going to go into the future, and we're going to see how this map evolved, how the color dots, diffused. And what we find here is that now, Chile diffused into all of these fishing products and into all of these processed food products, including the vegetables and the fruit juices, because basically they are diversifying toward related varieties, just like our knowledge diffusion idea would explain. Because of the lack of time, I'm going to skip, showing a similar example in DataViva, But DataViva is a tool that we build that makes available data for the entire formal sector of the Brazilian economy. This is data for 50 million people, every industry, municipality, product, and occupation in Brazil is here. It makes 1 billion visualizations. And since we were talking about extractive industries in the last presentation, I'm going to make only one point, which is in Brazil, extractive industries represent 22% of exports, but they employ only 261,000 people. Processing industries, on the other hand, also represent roughly like 25% of exports, but employed 8 million people. That means 32 times more people. So also we can even look in this case at the income inequality, of that industry, and we find that the income inequality of processing industries is 0.44. That's their Gini. In the case of extractive industries, is much higher, is 0.56. So that tells us that also even the mix of products that countries make, and we have a paper that's coming out on this, is even conditioning the level of inequality that countries have, because there are some industries that are basically non-inclusive, even though they can generate a lot of revenue, like the extractive industries. And the last fact that I'm going to talk to you guys about is that of economic growth. And I'm going to go very quickly over the history of economic growth, which starts with Adam Smith, saying that eventually, economic growth involves the accumulation of the things that we've done in the past, And in his language, there were basically two things: people and machines. There were labor and capital, In the 50s, Robert Solow mathematizes these theories, by saying that, well, people have kind of like a savings rate. And if we create a set of couple differential equations in which people are saving some of the things that they're producing, eventually that saving rate is going to determine the rate of growth in the long run and the equilibrium level of income of a country. The problem is that Solow model that include only capital and labor did not measure up very well with the data. There was a big gap that was left between the empirical data and what the model predicted. And as usual, in science, what that gap does is that it motivates other people to do work to try to fill that gap. So in the 80s and 90s, people like Paul Romer and Gregory Mankiw said, well, it's not just people and things, it's people and things and the knowledge that people have, because people need to know something. So there has to be something like human capital and education. And they include that, and they're able to close that gap a little bit. And then people like Putnam, Fukuyama, Coleman, and everything, they were saying, well, but people have to be able to connect, because if you have a lot of smart people that are assholes to each other, this thing is not going to work either. So also, you need to have social capital. But what we can do now is, in the context of economic complexity and computation, we can try to reinterpret those things to realize what was missing. So imagine here you have like two firms, and these firms are exchanging products, which are crystals of imagination in our new language. And also, each one of these individuals has some individual level knowledge, which is human capital. And people need to have links, so they need social capital, they need trust. But what you're missing from this picture, and it's something that should become obvious, is that what you're not counting is the knowledge and know-how that you accumulate at the collective level, which is not a simple addition of the knowledge and know-how that you have at the individual level. And that is what I call economic complexity. And economic complexity is this collective computational capacity of systems, which does not only correlate very highly with GDP per capita, but the differences between the computational capacity of a country, as measured by economic complexity, and its present level of income, is highly predictive of future economic growth. So over long periods of time, countries more or less get what they deserve. Their income adjusts to their computational capacity. So I started this talk by saying that the universe is made of energy, matter, and information. But information is the one that makes the universe interesting. Information gives the universe its structure, its beauty, and its complexity. But for the most part, we don't know what information is and where it comes from. Hopefully with this talk, we got a little bit closer to that answer. We saw that in physical systems, information is able to grow because there are three loopholes that allow information to grow despite the second law of thermodynamics. This is that systems need to spend energy, they need to be out of equilibrium, you need to have solids that allow that information to endure, and matter needs to develop a capacity to compute. But also, what we saw is that the computational capacities of systems is finite. And that finiteness is the one that makes the growth of information difficult. There is a finite capacity to compute in a cell, there is a finite capacity to compute in a tissue, but there's also a finite capacity to compute in a human, and in a team of humans, and even in a city of humans. And what this is telling you is that eventually, when you look at the universe in terms of computation and information, the distinction between the social science and the natural sciences kind of blur out. Because usually, from here, from this dude to the left, you would say these are natural sciences. From here to the right, you recast the human as the new social atom, and you have the social sciences. But if you think about the world in terms of information and computation, these are just different re-embodiments of the computational capacity of the universe that precede the human and then transcend us. And with that, I would like to thank you very much for your time.